In this section, we're going to look at additional topics for probability and for counting. We're going to start by looking at some of the counting ideas. And the first concept we're going to look at is a permutation. A permutation is an ordered arrangement of objects. Many times we're looking at how many different ways can a number of different orders of distinct objects be ordered. And to find this, we can use n factorial. Now, n factorial is something that is a concept that we see when we've been doing some of our conditional probabilities, where once we've removed an object, now there's fewer objects to select from. And so as we do our multiplications, they go down by one each time. So for example, when we talk about just n factorial, factorial is actually an operation, a mathematical operation, where we take n, so our first number, then we multiply it by 1 less than that number, 2 less than that number, so on and so forth, until we get down to 1. Now you can see by this definition that 0 would be problematic, because if we subtract 1 from 0, we're at -1 and then -2, and that wouldn't, we can't really have negative arrangements of objects. But 0 factorial comes about sometimes with some special definitions. We are going to look at how we actually use these here in a bit. But for right now, because some formulas end up with, as a consequence of the formula, a 0 sometimes, with a factorial, like in a denominator, we say 0 factorial is equal to 1. It's basically a little definition we created to make the formulas work for any numbers. So let's look at some examples. If I were to have 6 items, for example, and I was interested in knowing how many different ways 6 items could be arranged. In the first spot, I could put, the first spot, before I've laid down anything, there are 6 different items I could put in the first spot. But once I placed an item there's 5 items I have left that I could put in the second spot, and then 4, and then 3, and then 2, and then 1. So with this, we see this declining number of items each time, right? Because once we've placed an item, there's only 5 left that we could put in the next spot, and so on and so forth. Taking the factorial then, multiplying these numbers, 6 factorial, 6 times 5 times 4 times 3 times 2 times 1, gives me 720. There are 720 different arrangements that I could put 6 items into. So in other words, if I had 6 items, there are 720 different ways I could arrange them in a unique way. And these actually get pretty big pretty fast. 10 factorial, for example, that would be 10, 9, 8, and we'll just keep on going with that. 3, 2, 1, right? By the time we get to 10, and this is something we can actually do on our calculator. If you type in 10, and then type the math button, press the math button, and then go to PRB, which is along the top there. So you hit the right arrow to probability, PRB, and then choice number 4 is the explanation point. And so hit choice number 4, and you'll see the result is 3,628,800. 800. So 3,628,800 different ways, if I had 10 unique items, how I could arrange those. In a Sudoku puzzle, which some of you may be familiar with, we know that in the rows that we have, we can't have any repeating numbers. And it's always a 9 by 9 thing. 0 is not an option, so there's only 9 digits, 1 through 9. Also, we can't have repeating values in our columns either. And then within the little boxes, we can't have any repeating numbers, right? So for all of those, we have to have unique numbers in each spot. That's kind of the idea of the Sudoku. And so the question here is, The object of a 9x9 Sudoku number puzzle is to fill in the grid so that each row, each column, and each 3x3 grid contain the digits 1 to 9. How many different ways can the first row of a blank 9x9 Sudoku grid be filled? So that would give me 9 items in a row there, 3, 3, 3. So 9 factorial, really. There's going to be 9 and then 8, etc. Putting that into our calculator. You see that's 362,880 different ways. There are times where we don't go all the way down to 1 in our multiplications. And so then we have this type of permutation formula that we need here, where the permutation is the number of n objects that we can take r at a time. And we have this formula here, n factorial over n minus r factorial, where r has to be less than or equal to n. The number of different permutations of n distinct objects taken r at a time. Let's look at an example for this. Find the number of ways of forming 4-digit codes in which no digit is repeated. Now, we can kind of figure this out without using that formula, so I want to just give you an idea of what we would do here. If no digits are repeated, and it's a 4-digit code, there's 10 different digits that can go in the first, then 9, then 8, then 7. Now, the factorial thing makes us go all the way down to 1. So how do we create a formula that will give us this? And that's what the permutation formula does there. We have 10 objects, 10 different digits, and we want 4 of those, right? We only want 4 digits in our thing, our code. So this gives us n, so that's 10 factorial, divided by n, which is 10 minus 4 factorial. So let's see how this would work itself out. That's 10 times 8, or 10 times 9 times 7, times 8 times 7 times 6, so on and so forth, all the way down to 10 minus 4 factorial is 6 factorial. So, of course, 6 factorial is this, this number and everything less than that number all the way down to 1. So this and that would cancel out, and this leaves me with the 10 times 9 times 8 times 7, which gives us, multiplying those out, 5,040 different ways. There's 5,040 different 4-digit codes I could get if none of the digits can be repeated. Here's another example where we could use this formula. Each year, 33 race cars start the Indianapolis 500. How many ways can the cars finish first, second, and third? So we need to select 3 cars from a group of 33. So we have 33 items, and we want to select 3 from those. And we want the different orders to be considered for this. And I'll cover that here in a second. But this would be 33 factorial over 30 factorial. So that 30 factorial is going to cancel out everything from 30 and below, right? 30 factorial is going to cancel everything below that out. So we have 33, 32, 31. If you multiply those out, we actually get 32,736. So of the 33 cars that we have, there are 32,736 ways that I could pick 3 cars that are first, second, and third. Notice that those would be distinct positions, right? First, second, third. Let's say we had red car, blue car, yellow car. But there's like, all the different colors of the rainbow there. So we had red, blue, and yellow. We would count this as a separate count than say blue, red, yellow, right? because they have places. So these would be two of the ways of these 32,736 different permutations I could get from this group. This is going to become important when we distinguish this formula from another formula. Another type of permutation is a distinguishable permutation. A distinguishable permutation is the number of distinguishable permutations of n objects, n being the total number, right? But we have them into types. N1 is one type, N2 is another type, so on and so forth. And so however many types we have, we put those in the bottom, and we take their factorial each. And then the total is the just total number of objects that we have. Let's look at an example of this. So here a building contractor is planning to develop a subdivision. The subdivision is to consist of 6 one-story houses, 4 two-story houses, and 2 split-level houses. In how many distinguishable ways can the houses be arranged? So we have them along a street, right? How many different ways can they be arranged? All in all, there's a total of 12 different houses, right? We have 6, and then 2 split levels, and then 4 two-stories. And so we know that the top number, n, is going to be 12 factorial. Then we have 6 one-story houses, so that will be one number on the bottom. This is my distinguishable part of it. We have 4 two-story houses, and then we have 2 one-story houses. So putting this into our calculator, if you do this all at once, which you will probably want to do, you want to put that whole thing that we have in the denominator in parentheses. Otherwise, it'll just divide by the first number you have, and it'll end up multiplying by the other 2. Try putting it in this calculator right now. The answer you should get, if you're doing it correctly, and it's important to know when you are and when you're not doing this correctly, is 13,860. So, with all of these different types of house, lining them up on a street, there are 13,860 ways I could distinguishably arrange those different houses. For this next part, we're going to look at the other more important thing, which is called a combination. And a combination of n objects taken r at a time. This sounds a lot like a permutation, right? So we have n objects, and we're going to take r of them from a group of n. And when we take those, we're not going to take order into consideration. When that's the case, this is the formula we're going to use here. It's a combinations formula. And the important thing to remember is that order isn't important. So I'll give you an example to contrast this with the permutation. Let's say that we have 12 students. So I'm just going to write them here as circles. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12. Let me make sure I have that. Yep. 12 students. And we're going to select a committee, right? A committee of 3 people. And this is going to be our classroom committee. And they're going to make decisions about certain things. Now, because they're on a committee, order really isn't important, right? It doesn't matter if you get selected first, second, or third. It doesn't really matter. There is no order to those 3 students. So so if I select them in different ways, like I select student A first, and then B second, and then C third, that would not be any different than selecting B first, C second, and A third, right? We would not count that as a different combination because it's just 3 people, 3 objects, and there's no order to them. So this would be 12 students taken in groups of 3, where we take 12 on top, and then we have 12 minus 3, which is 9 factorial, over 3 factorial. That extra division by 3 takes out and doesn't count as a separate combination the same group of 3 students, just picked in a different order. Again, if you're putting this into your calculator, you want to put parentheses around that bottom. And you should practice putting this in there. But doing that, that would give me 220 different combinations of committees that I could create from those 3 people. There's 220 different committees of different students, each unique, right? Never the same 3 people in each that I could create. Now, let's take the same example and say where it would be a permutation. We would do it as a permutation if we were selecting a president, vice president, and secretary, right? So if I have student A here, B here, and C here, that would be a very different combination if we switched A and C, right? Because now I have a different president and a different secretary. So we would want to consider that as a separate count, whereas the committee, it really doesn't matter what order they're selected in. So a permutation takes order into account where combinations does not take order into account. So 12 permutations of 3 gives me 12 factorial over 9 factorial, which essentially is 12 times 11 times 10. And 12 times 11 times 10 gives me 1,320. So when we're taking position into account, when order is important, we're going to end up with more counts than when order really isn't important. I just don't want to count these same 3 people differently if they're selected at different times. That's the difference between a permutation and a combination. Let's look at another example. A state's Department of Transportation plans to develop a new section of interstate highway and receives 16 bids for the project. The state plans to hire 4 of the bidding companies. How many different combinations of 4 companies can be selected from the 16 bidding companies? So again, there's 16 and we're going to take a group of 4. We're going to take 4 of them out of there. We want to know how many different groups of 4 could we have. So there's a group here. There's no real order to those 4 groups. If you're one of those 4 companies, you're going to be happy if you get selected, and you won't care whether your name was called first, second, third, or fourth. So this is a combination situation. So we have 16 groups of 4. So this is 16 factorial over 12 factorial multiplied by 4 factorial. Again, putting these into parentheses. Now, I do want to show you that if you type in 16, so type in your calculator 16, and then I want you to go to math again, and then PRB, so the same screen, probability. If you look at choices number 2 and 3, number 2 says NPR, and sorry, that's number 2, says that, and number 3 says NCR. That is the permutation and the combination. So if I typed in 16, if I select number 3, the combination, since this order really isn't important, and then I type the number I want, which would be 4, this will do the combination for me. So on your screen, some of you, if you have an older version like the one I'm looking at right now, it says 16 and then it says NCR and then you type 4. For more recent calculators, it actually puts these numbers into those places. But even if it doesn't, this is going to the N and this one's going to the R. And then you hit enter and it'll give you the answer. The answer here is 1,820 different combinations of 4 companies that we could have or we could award with this contract. Let's look at what this can mean for probabilities. The Student Advisory Board consists of 17 members. The three members serve as the board's chair, secretary, and webmaster. Each member is equally likely to serve in any of the positions. Let's just say they're randomly selected. What is the probability of randomly selecting the three board members who will be chosen for the board? So let's say that you are going to guess on which three you think will be chosen for the board. Now notice that these have positions. We have the chair, secretary, and webmaster. And so order is important. In this case, with 17 permutations with three positions, we would want to take 17 and divide it by n minus 3, 17 minus 3, which is 14. And so that gives me 17, 16, 15. Or you can use the permutation function on your calculator. This will give me the number of ways, or the number of different combination or permutations, really, that I have here. And we get 4,080. So this is the count of the number of different ways, different groups of three that I could select from those 17. Now, all of these different combinations, if you're going to guess, the probability of your guessing the three members, remember, because they have positions, there's only going to be one out of those that you could possibly select out of those 4,080. So from those 17 members, you have a 1 out of 4,080 combinations or permutations that you could get. This would be a 0.00025, 245. We'll put 245. So that's a 0.0245% probability that you'd be able to guess that combination. Find the probability of being dealt 5 diamonds from a standard deck of 52 playing cards. So if we're being dealt 5 cards, we want to know what's the probability I could get 5 diamonds. So one of the things we would want to figure out is how many different combinations of 5 could I get from 52 playing cards. This will be, in other words, I want 52 cards, selecting 5. How many different combinations of 5 cards could I get? There's no order to these cards, right? If I got the 2 of hearts first and the 5 of, whatever hearts next, if I had switched those 2 around, that's the same hand of cards, right? So there's no order to these. So 52 combinations of 5, 52, math probability, NCR with 5. There are a lot of different ways that I could have 5 different cards. 2,598,000. Oops, I put 89. 98,960. This is the total number of hands that I could be dealt. 2.5 million, or 2.6 million, really close. Now, with the 5 diamonds, there's 13 diamonds in a deck. So if I'm looking at those 13 diamonds that are in there, how many different combinations of diamonds could I be dealt? I keep on putting 52, but there's 13 diamonds. And I'm going to hopefully have 5 diamonds dealt. So we're interested in how many groups of 13 diamonds I could get, how many groups of 5. Putting that into the calculator, we see there are 1,287 different combinations of 5 diamonds I could be dealt. So the probability of getting 5 diamonds in a hand would be 1,287 over 2,598,960. So dividing these two things by each other, we get 0.0005 5, which is 0.05%. So 5/100ths of a percent chance, way less than 1%, chance that I would get 5 diamonds in a row. Now, there's another way we could do this as well. Taking it from a probability standpoint, we get a diamond followed by a diamond, 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 and diamond. Well, there's 13 out of the 52 cards that are diamonds, 12 out of 51 now that I've selected a diamond, right, using dependent probabilities. So we're really just doing this same thing. If you multiply this out, you'll see this gives us the same result, right? With this number, I would get these guys down here. And this number is what I would get with these up here.